Hello and welcome to another stream. How's it going? Right. So, today we're going to carry on with the Voxel map data structure. And I've got a plan, which we'll go over. Just making sure the stream is running. Because looks like it's running, but looks like it's not at the same time. Right, it's running. Cool. Lovely. So, welcome to the stream, everyone. Appreciate you all coming by. Welcome to another stream where we try and make a game from scratch in our own engine, and the game working title is called Man Shall Not Live by Bread Alone. You can go and check out the YouTube channel for the game pitch. You'll find it on there somewhere, depending on how far in the future what you're watching this. But there's a Discord channel as well. I'm going to come and hang and chat. In the meantime, I'll stream, ask questions, or get involved in any conversation around programming or the Bible and stuff like that. And also we have a Ko-Fi if you enjoy the streams, want to kick some support towards the studio and the mission, you can find a way to support over the Ko-Fi and get access to the code to run on your own local machine. But today we're going to be working on the voxel map data structure. We've been trying to work on it such that we can have a very big map stored all in memory, but it doesn't look like that's entirely possible after doing some like napkin maths basically. And we was going to go for a more of a complicated data structure. We have like a variable amount of bits per voxel, and you do that by having a bunch of palettes everywhere. But it looks like it doesn't give us that many savings. It looks like it gives us 2 times, somewhere between two. The variable amount is about half as big as 2 bytes per voxel, basically. Kind of. It just depends. So we might as well just do 2 bytes per voxel, so you have up to 64k materials per voxel, and that's basically the idea. So yeah, we're just gonna have a very simple 4x4x4 node tree, right? So it's like a sparse voxel 64 array tree rather than a sparse voxel octree, right? And the leaf node is just going to point to 2 cache lines of voxel material indices. So they'll be aligned to cache lines, and yeah, that should be good. So it all should be quite efficient in that regard, but the issue is it's going to use a lot of memory. So we probably can't reach this target of a kilometer by a kilometer by a quarter of a kilometer of a map without doing caching to disk and loading it in. But that's something that we'll add later on, because we'll just add that in later, right? We want to get stuff rendering on screen because that's much more exciting. So we'll have a global palette of 64k for the map only. The models will still have material palettes, little custom palettes, so you can swap out colors and stuff and still use the same model. But yeah, and the leaf nodes just point to, the leaf node is now just pointing to an array of voxel material in index data, which is always 2 bytes per voxel. That makes stuff incredibly, like, far more simple to work with, and it will mean it will use about 2 times to 3 times as much data memory as the other one, but it'll be far more simple to implement, and we can make up for its shortcomings by just caching stuff to disk, right? And you'd have to cache stuff with disk to disk anyway with the variable amount of bits per voxel. So Code is more simple, and you kind of have to solve the same problems anyway. But yeah. Right, so we move over to the Voxel shared, and Coda will start here and make sure this is okay. I think I've already kind of changed it a bit, but we'll yeah, but then we've got to change the pool and get rid of the block basically. But right, let's do a prayer, then we'll get started in the program. And yeah, if you have any questions, feel free to ask away. Father in heaven, we thank you, Lord, for this day. We bless your holy name. Thank you, Lord, for your Son. Thank you for the sacrifice, the only sacrifice which is worthy. Thank you for the blood. Thank you for providing us a way to be saved apart from the law. We're so blessed to have this in this age of grace to be living in. Thank you, Lord, for putting us here in this time where the gospel is so available and is so well known. And thank you for, giving us the lives that we have and the peace we have in our lands. And thank you for my wife and my children. Thank you for preserving all these people here who are watching the stream and keeping them alive and giving them the grace and mercy. Lord, we just pray for your divine touch on our lives, Lord. Send the right people in our lives to take us to the next places. Put the right people in our lives to keep us on the right path with you. Lead us into paths of righteousness for your name's sake, Lord God, and help use us for the kingdom of God on this earth while there's still time. And Lord, I pray that each and every one of my viewers gets to know you before the time is up, because Jesus Christ can come back at any moment and you see all the pieces fitting in place. And maybe that day is very soon, but we don't know. But we just pray that before that time is, at least everyone knows enough information, or they are saved by the blood of Jesus Christ before. Thank you, Lord. We worship your holy name. In Jesus' name we pray. Amen. Cool. Right, so we used to have, like, in the last stream, we end up so it was a little bit more complicated, right? We wanted to have, like, so a block is 16 by 16 by 16, and that's like our basic unit of like 1 meter. 16 voxels cubed basically. And that's where the palette used to be stored, but no longer do we need a palette because it's just a global palette. So it really just simplifies everything. So we have a node hot structure, and this is going to be accessed all the time, and a node cold, and this gets accessed when the node gets hit, right? So when when the node gets hit, it can then look at the cold data and basically find where the children are in the node array and start accessing the children from there basically. So this will only get accessed when stuff gets hit. So less stuff will be pulled into cache lines and GPU cache, and therefore more stuff will fit in cache and be reused. So effectively, nodes are always aligned to cache lines, and say if there's only say if you have a node hot or whatever and you hit it, you can call this one the parent hot, parent cold, right? And so you end up traversing through those children exist bits and finding a node which is, in this 4x4x4 node, you find a child which is active and you hit it with a ray. Well, you would then go to the cold parent data, get the auxiliary, that'll point to where the children are, and the children, these are the children here, let's just say there's only 5 children which exist, there's only 5 bits which are 1 inside here, there would only be 5 which are allocated, rounded up to the nearest cache line. So, these are 8 bytes per element, so you have 8 of those in a cache line. So technically it gets rounded up to 8, right? And so this allows us to make sure all of our data, all of our nodes are aligned to cache lines. So when you're accessing the children elements, they're all, you won't access, as soon as you access one child, its siblings are loaded into cache for the most part. And yeah, that's quite handy and pretty cool. So we want to be able to do a similar thing where we'll need, now we'll leave this alone. Right, so we go over to the Voxel internal. What we'll find is we can get rid of this block thing now, and we'll just call this Voxel material indices. So these are the types of things that we can free, and we'll just get rid of the blocks here, and Voxel material indices, and those would be U16s. Okay, cool. So we also get rid of the block allocator. It's so much better. We don't need to say if it needs a new allocation because they're not being resized, they're just fixed sized. Just keeping it simple. Right, so now we just want to look around and see. So this is like the internal global pool where you can just allocate nodes and stuff. So, theoretically you can allocate multiple maps and it would all just, there'll be a global sort of storage in the background, which is pre-allocated pools of data basically that it pulls from. And so what does that 8 mean? I've just divided by 8 and I don't know why. So a number of allocations would be that divided by 8. Is that true? Nodes cap divided by half. You definitely want it for that. Right. That's the number of allocations you'll need. But divided by 8. Oh, right. Yeah, because that's how many you fit per cache line or something like that. Right, we'll just throw a const thing in here or something. Const. Right. So we'll say something like site what are we saying? We're saying like minimum sibling nodes. So that'll be size of let's go uppercase these days. All right. Completely forgot that. Thankfully, Helix is very easy to find this sort of stuff. But yeah, anyways, so you get the biggest node. So it's the voxel map node hot. And I guess you pick the max between the hot and cold, right? And then you divide that by the number of like the size of a sorry, you do a cache line size divided by that, yeah? So that's the minimum number of sibling nodes that you can have, right? When you allocate one, you'll get at least that many sibling nodes. So if you do nodes cap divided by the siblings, that will then mean that's the most number of allocations basically that you would have, number of allocations you would have when you want to allocate this many, when you have this capacity for nodes. Round up though. Cool. So in terms of like the number of voxel like the voxel material indices, you have one of those allocated at the final 4 by 4 by 4 at the leaf node. So you've just do a divide by 2, that should be fine. The number of allocations, but yeah, let's carry on. So no longer is there any block. Cool. So this can go here. And so can this one. Because we don't need to grow these. Or maybe grow them if they span over a cache line or not. Allocate. We do allocate these. Voxel material indices. Oh, that was a copy paste error. I'm glad we found that. Very good. So that will give us so we can just do a size, I guess. I don't know. Well, the element size be a U16, but I think we shouldn't pass in a size. Because it's fixed anyway. Can always add it back in if need be. So the size is going to be it's going to be size of U16 times 64. Will it be? And that's the element range. Yeah, because it goes into U32 is the lowest size you can do. Okay, that's very good. So deallocate the last function to change. It's here. Right, so now that the allocation stuff is sorted out, we can now go to the map, basically. So, oh. Cool. That'll be a U16 though. No, I don't think you need... This should be based on the node. Right, nodes cap times 64. Right, so we should probably say number of leaf nodes. That would be another yeah. So number of leaf nodes capacity, nodes cap divided by 2. So that is what we're looking for. Okay. Oh, that changed. So that'll be, okay, I guess you'll put that into a local again. Hang on a minute, these are supposed to be in bytes. I'm glad we sorted that out. Okay, we found another bug. So these are supposed to be in bytes. So capacity in bytes. So the alignment is a cache line. So that would be times size of. So I guess we want another one of these to be called like the max node size. Then this one will be times U16 or something like that, but or I could do size of U32 because that's the smallest allocation you can actually do anyway. Yeah, but now we'll do U16. It's fine, it's aligned to U32 anyway. Yup. Cool. Right, any more compile errors in this code? No. Right, so now that's like very simple. That's cool. So the thing we want to work on next is the public interface, which is that sort of voxel map. This is the complicated thing was trying to get working. We end up calling it like a voxel map mutator because it's got to allocate this extra sort of like, has this node been mutated this frame? And so ideally you can pass in any map into there. And then, well, yeah, it's a bit weird. Yeah, perhaps you should be able to get back a voxel map, which is just a read-only version of it. And the mutator is one you obviously, and you want to be changing it. Something like that. Unless you can call one of them a voxel map reference. And that will be or voxel map view, right? So a way to view it, something like that. Yeah, it should be a lot easier to get this done now. We're just in a simple 64 child tree, right? 4x4x4. So the code to get the voxels set and unset done would be a lot easier. So I wonder if you should just call this a view. Like, you know, this is what the GPU gets, isn't it? So maybe you can just call it voxel map GPU, and then you send the other thing around. But this thing, only the game thread is going to have, right? And it can, hey there, Valabus, welcome back, sir. God bless you. Then if the if U16 now, we need to divide by U16 in the allocator. That is a good question. Thank you for catching that. So you're thinking about it here, right? Yeah, technically, maybe. Wait a minute. Make sure you're not thinking somewhere else. Yes, this gives you a byte range. So this is an element range. I know it says U32 and it does seem wrong. Yeah, but on GPU it's only. Yeah, you know what? You know what I should do? I should just do. It's so damn confusing. But yeah, I'm not sure the cleanest way to make this code, but it should probably be like this code is correct and will work fine. It's just we should probably. So what it is, do 32s instead, right? So no. So yeah, 4 times 32 is that's 2 cache lines, yeah. Man, it's so damn confusing. But yeah, we'll do U32 pairs, right? So U32 a pair of indices. That's the minimum unit on GPU, and then that way it will make this code more consistent. But it is confusing, even if you do U32s. Or now it's still U32s. So here when we divide just U32 times. Yep. Right, that's good. So it gives you an element range. So you got these element ranges and stuff. Just got to be careful here. These don't multiply the ranges again. So when we come and pick up at the frame initialized to deallocate it properly, like 7 frames later, they're going to be the wrong ranges, right? So these need to be multiplied back into the right ranges. We need to get that as a constant somewhere. Anywho. Nice. Right, thanks for that. Help me find that bug. You look like an MMA fighter, fair play. You might have chosen the wrong profession. Maybe I am like 6'5", 6'6". So if I put on enough muscle, maybe, but I got quite a lot of joint problems, so you know, they probably got enough muscle. They probably won't be a problem anymore. But anyway, but I ain't chosen the wrong profession. Yeah, problem with that sport is you need to be very smart about it, right? Because it's very taxing on your body, and also it's quite difficult not to sin at the same time. Right, back to the public interface. So, Voxel map mutator. So this is only owned by the game thread. The render thread isn't really going to have this. It's going to have like that sort of read-only version of it. So I guess keeping it as a mutator is fine. You know, it might be better just to inline this stuff here, right? Because you're not really going to be using that in a structure anyway. So yeah, I think that'd be fine. So you can have a way to basically get the map, you know, get the map like that. That's the old one, isn't it? But yeah, we'll sort that out. So this is all the complicated code we was trying to do before. But I think we can just delete it now. But yeah, we was trying to do variable amount of bits per block, and it was adding a lot of complication, and it would only will save half the amount of memory in RAM and VRAM, right? And we would save, or maybe like a third of memory. But we'll still have to probably put stuff out to disk and load it in, right? So we might as well just do the easier version, right? The less complicated version, because then the code is just a lot easier to manage. So some of this is still staying though, so it's not like we're deleting everything, but just be more manageable. So, right, we keep traversing down. So we come in, we divide by 4, we figure out the child coordinate, so it's like 0 to 4 exclusively. And then we look at the child index 0 to 64 inclusively, sorry, exclusively. We work out the packed offset by looking at how many children exist, and that gives us a packed together one. So effectively all the children which are not allocated, those don't represent, they're empty space in the array. So everything's tightly packed next to each other. So when you add a new child, you have to shift the elements along. Now, right, a lot of this code still stays. A lot of these if statements do as well. Yeah, this still stays, but the else section is, it should, I think it should just be returning the leaf. But then, no, I think we've got to allocate the leaf. Hang on a minute. If the child node is missing, what does that even mean? Or needs copy. So if you're on a leaf node, meaning you're the final 4x4x4 or whatever, yeah, how do you know whether to make a leaf as well? That's another thing. Yeah, you got to know how to, at what point to make it. You probably need a depth parameter. Well, you don't need a depth. Well, with a node dim, the node dim will be the size of the map. Oh, right, you don't even need that passed in. So you would literally do this. And you don't even need that as well. Right, get in there. Get in places. Okay, so node dim. The max elements that, so, you know, let's say it's 1024 by 1024 by 256, so it'll be 1024. So is that what you want though? Yeah, yeah, it is. So you have a max depth. So you want to get like equals node dim divided by 4. So, you know, there's these 4s dotted about, but you know, not really the right thing. We should be doing this node dim. Right. Okay. So that's the maximum depth. We should probably assert that node dim is a multiple so map dims must be a multiple of. Now this should probably just go in the initialize function so we don't keep calling it all the time. Work that out. Anywho. Now, so that's the max depth. So when we reach that depth, so you would just do depth. And there shouldn't be any continues as a return though. So depth equal this. Now we could just call it probably node depth. Is that really a max node depth though? Like, here's the way to work it out, right? Say if the map size is 4, right? That's 1 4 by 4 by 4. So you've only got 1. So yeah, be 4 divided by 4, so it's 1. Then you come into node depth 0 or node depth 0. Like that is the leaf node, right? So when you're trying to allocate something, like a node for this or whatever, that is the leaf node, right? So yeah, you want to probably do a +1. You know, you could just do a take 1, basically. Yeah, let's just do a take 1. That'll be it. Or equal to okay, so let's just write some of this code out, the new code, and we can So effectively, huh. If cold is leaf, but it never set up. So, right, so you start at the root node or whatever, and you find in here if this child is missing or not, and you insert that child into there. And the cold will be the parent, and you're finding, right, so is zero initialized, right? So when you end up locating child here, yeah, so maybe you don't want to do that. So that would, so I think you'll get to a certain depth, basically. You get the child, and you'll go increase the depth. So now you will come across, yes, you eventually will come across a leaf. So and you can know that based on the node depth. And so you could store the is leaf right when you get there. So say if it's just allocated it here, and you're finding find node and copy if need be. Yeah, so it makes a complete copy of the tree as it goes down if need be. And at this point, yeah, maybe you just say, right, so Boolean is next, is child a leaf. So that will be node depth equal +1 equal max node depth. So now when you allocate, move this out here. If the child is missing, so they're always going to be 0 at the new child nodes, which is fine. And if the child node is a leaf, we could probably find the cold here and just store in there that it is a leaf. So something like voxel map node cold is leaf set. That's a code generated function, and we just set it to true. Now the thing is, you need to find another place to allocate all those, like the other Yeah, so here, when it tries to allocate the children, it updates the cold auxiliary, which is the pointer, basically, the start index. So yeah, maybe we can change that to just mean start index, but yeah, you want to allocate here as well. So voxel pool so you allocate me some start indices. Sorry, some voxel material indices and return to me the start of that probably. That's probably sufficient enough. Okay, so that will be byte range. Now, if we start, it'd be E start plus that. Oh, and the plus size of E32 times 32. There we go. Cool. Right, that'll work. So where was we? So yeah, that's just a start index basically for the voxel material indices and that voxel material indices array. The sub allocator from there using the fixed align heap allocator. So it's always aligned to cache lines and stuff like that. Yeah. So the next thing to look at is, so if the child is missing or it needs to copy it because we're doing a copy on write, it will perform a copy of that node. And then if it works out that the child is a leaf, we need to so we'll call it child code. The voxel map node code. So we got the child that it's reallocating the child array for and shifting stuff along, and we shall say it's a leaf and set the auxiliary to point to that voxel material array. All right, that should be a lot better, and that works. And then what we want to say is, like, at this point, we have found a leaf, right? And so, but that's only if it's missing on these a copy. So it goes around. And so I think we just say here, right? If node depth less than when it's equal to max node depth, we will just return node index at the end. Cool. Right, so that function is somewhat done now. It does all the copy and write stuff. There's still some things though which it doesn't do. Should probably look into fixing some of those. But basically when we call voxel set, we can now just call into this and it will traverse that whole thing. Something to be wary of though is we'll traverse through that whole thing and then we should be able to basically set the material index. So we can just do something like I think we can just use 16 in it, but right, I'll have a look at that. Thank you, sir. Right, let's have a look at that. Node depth plus. Is that available for like the shifts? Nah, it's not actually. So arithmetic is always done first. Yeah, so you can do that stuff. But yeah, when it's the bitwise operators, basically you gotta be like very careful with those. Yeah, so so stuff like this I think is that has a lower precedence than equals. Yeah, so it tells you there's a problem. Yeah, it's pretty bad. So it's all the bitwise stuff basically. A lot of the time, not all the time, but yeah, so the AND or an XORs, yeah. But yeah, fun. Fun. So to finish up this voxel set, so as you can tell, it's quite expensive. You've got to like traverse through the whole thing from top to bottom just to set a voxel. So there'll be a way to actually do this quicker, and do groups of things. But for now, I'll have the slow way. But yeah, so we would want to find. So you go to the pool and get the cold data, and you can extract out the auxiliary. So that's we can call that the materials, voxel material start index. I'll just call it start index, right? You get yourself where's the pool? So node index. And then you can use that to access pool voxel material indices. And here you go, start index. So now you cast it into a U16. It is really dodgy, but thank you, GPUs. So there's your voxel materials. So you call it the node materials. These are those things. And now you just got to figure out, right, within this, how do I access it? So there is a thing you can do. child index from this coordinate, so divide by the dim. So the coordinate kept on getting divided by 4, basically. So I think we're looking at doing a mod 4 now, something like that. We'll figure it out. But yeah, so if we've got a coordinate, we want like yeah, I think you want to do a mod 4. Pretty sure about that. Maybe you can just AND it, I'm not sure. But a mod would be safer. So you'll get the child coordinate to be 0 to 3 inclusively. And that would be, then you use the Morton code, right, to get it from a, because that's where everything is stored, right? It's Morton swizzled, the Z curve. If you're not sure what that is, just throw into Google and see images, you'll see what it is. So as we increase the index, it goes in this Z order. So everything's more tightly packed and around stuff which is closer in 3D space is closer together in a linear index, basically. And that is the position where the material goes. Voila. So I think that should be it. I think that's the code. Now, yeah. So maybe, like, could this function return something that's better? And maybe it should be called, like, find leaf, basically, right? Find leaf node. It's not really find node, but yeah, find a leaf node. And ultimately you're using node index to what, right? So you could just get it to return this start index and you know, you could also get it to return basically the pointer to the materials, but then it won't be really reusable for anything else, will it? But yeah, stuff to think about. So there's set and unset. Unset will basically just set it to 0 though, so unset shouldn't really exist. And a get, do we even do a get? Right, then I made this internal function here, basically, so unset will go. Now get is basically the same, but we just want to traverse. Yeah, so I think we're going to call this maybe like find leaf. Find leaf. Excuse me. Yeah, so I think you are interested in some of them returning nodes. Like I think we'll make a function to help us like I think this should be usable by another structure which will keep a cache of nodes, so it doesn't have to keep traversing down the hierarchy. It could probably cache the last one that it knew about, maybe, or the last two, that sort of thing. Maybe. So we'll put this here. This will be the internal. I forget which way I do it. Sometimes I do internal first or public stuff first, but this is some old code that I think I might get rid of down below. Is this useful anymore? It's just some old code from a previous version. We've tried this a few times. Let's get rid of it. I think we don't need it anymore. Yeah, so this be like find leaf node mute or something like that. And we'll have a immutable one. Or for write, then find it for read, right? A little bit more explicitly labeled. So and we are probably going to make them start from a particular depth as well. We'll figure that one out. But yeah, so I reckon, so this one doesn't do any creating. So if it cannot find it, it's going to return E32 max basically. So what are we doing exactly? So if it's missing, so if it doesn't exist, then we return U32 max, yeah? And then all this needs copy stuff and all this, la 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 la, goes away. So why is that supposed to be less than 4? So yeah, I'm a bit confused now. Why is that supposed to be? So coordinate is just anywhere on the map, like a voxel index space, you know, voxel coordinate. So every time you divide it by 4, that's obviously going to be, right, I think you meant to mod it. Right, then in this case that assert shouldn't even be there. But modding it doesn't make any sense. So the node dim starts off as the map size, right? 1024, right? Big number. And you want to figure out which subregion it fits in, right? Of the 4x4x4. So you're dividing it by 4, the node dim by 4. Oh, sorry, right, you're dividing the node dim, the coordinate by the node dimensions, right? So it's 1024 divided by 4, 256. So you're doing coordinate divided by 256, right? And that'll, okay, I got you now. Right. I see. Pass me has got it. So, right, we're in a good place. Anywho, so that's just gonna do all that sort of stuff and keep going around and voila, amazing. So where does it say, oh yeah, no depth when it reaches the child. Good, 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 amazing. Now, so that one can be used. I think we can have like convenience functions, basically a way to access just the material data right up maybe, or nah, maybe not. Yeah, I think we want another one of these. This is a 4 rights, isn't it? 4 right. Got to put these. This be a 4 read. So node Now, if the node index equals U32 max, we'll just return a material index of 0, which should just be air, right? Should be empty space. So that's looking at returning whatever that is. Okay. So we could make another function which would say basically, you know, no, I think it's fine. Right, but we want to assert here maybe that it is a leaf. So auxiliary assert is, here is leaf. Something like that, just keep it safe. So that'll be here. Cool. Okay. Right, getting very close now. What to do next? Yeah, how do we like delete nodes and stuff like this? Yeah, we might want to traverse from a particular point, but I guess we'll leave that for later. Let's just get these in the internal header file. Hey there, a pillar. Have you written any ray tracing based shape based renderers or rasterization only? So, I've done ray tracing in Compute in the past. I've done, we did like a sphere and then an ellipsoid renderer, using Compute only. Tile binned objects, so binned the spheres and that into screen tiles, and did a Compute-based renderer that way. So you could have seen it as like a particle render in a way. What else? But yeah, I've used like the ray tracing API and that before as well, so it wasn't just Compute. But yeah. How about yourself? Have you used the ray tracing, or have you done any ray tracing stuff? Not specifically the ray tracing API, but just any ray trace renderers. Alright, so yeah, let's just pop this in here. Cool. Ah, fun leaf. Cool. Right, so I'm glad that's in a better place than it was. So let's get this thing called a voxel map, so we can just call it M. Right, it's more of just a reference than something gets mutated. So M, well, you know, dims are equal to map dims and the root node. Okay, lovely. Now, we still got some issues with this, the way this works, but it's getting closer. So handle, what is this one? Handle leaf node copy and write. No, that's done now. That's gone. No longer relevant. Yeah, how do we delete nodes, right? So like if you store a bunch of the same, say if the leaf node is just air, right? Now you can delete some nodes, right? That is a good question. If the thing is just air, can delete nodes. So we probably need to make another internal one. You can just probably call it. Yes, when you do a set. So you probably just say, right, if this is air, have I got like a mem? No, I ain't got one of them, but yeah, basically mem compare. Nah, just spin over it. Or empty, maybe. So we'll spin over this, the 64 elements. Children capacity 64. So we'll spin over all those and we'll simply go over these no materials, and if any of those are not equal to 0, is empty is equal to false, and we break. Now if is empty, it's where the deletion begins. So we literally just want to delete everything up. Now, so we should probably again make that into another function, because there'll probably be another API which will cache some of these nodes and stuff. Maybe. We'll put it into a function. So we'll call it voxel map mutator delete or remove leaf node. So we're removing. Now the thing is, if you remove leaf node, the issue is you gotta like we don't have parent indices. Like we just don't do that. So you literally got to scan down the whole tree again, right? Which is probably not that bad, right? It depends how many layers there are, but oh, what have I done? I brought up the AI. Goodbye. But yeah, so there's 4 times 4. Come on. Yeah, so maybe it's too many. One too many. Right, so 1, 2, 3, 4, 5, 6, 7. So 7 indirections basically to get to where we were, and then possibly wind back up the stack again. And yeah, so I guess she's passing this, right? And it's quite an easy function to write. So it's like this one. Well, I say it's easy, but maybe I'll speak too soon. Let's find out. So you traverse until you find your leaf, but you also keep a stack, right? So so I guess you can use like kind of like temporary allocate this thing. Allocate me an array of U32. And we'll go up to... So how'd you work out? So it was 7, wasn't it? So I think you do... So we did that 16k number. On... So 4, 8, 12, 13, 14. Right, so it's log 2. It'd be like log 2 divided by 2. Something like that. So you can just do a most significant bit index. So take 1, most significant bit index. Well, so that'd be bit MSB. Right, so log 2 basically, then divide by 2. So it'll be... Yeah, so that was like 14, so it'd be 7, just as we saw. So you have like 7 parents or something like that. And then we simply just, as we're going along, poke this thing in here. You just go node depth. Cool. And it should exist. Right, so we're going to do an assert that it exists. Maybe. You know, we could just return a boolean, right, to be like whether we did it or not. Maybe that's sufficient enough. So if it can obviously locate it, problem. So again, we've got these asserts in here and all that, but fine. What's this one? Okay. So when we get here, we should have found it. So we should assert that it is a leaf. Now, that's a good point. We could have just, these things here that we're doing, those could be asserts inside these functions, but then again, yeah, it should be. So that should be there. And then same here as well. So, right, so when we get this leaf node now, you can definitely remove this one. You want to go up to the parent and then modify the bit set. If all of those bits are 0, then it just reminded me. this is not as good. Like, this should already be using the bit set. If not, what's the point? Yeah, so we need the hot array as well. There's like a voxel map. What do we call it? Like voxel map shared. It's in there, isn't it? Shared.h. Right, what we got on here? We got node child exists. Yeah, I wonder if we should have a way to. We've got to have a way to modify this. Again, another function. Yeah, it's got to be something like voxel map node. Yeah, when did we ever sort of mark these? I don't think we have been marking these at all. Right, we should do that. So anyway, we get the hot. And we want to like poke that in there. So I guess you can do a set or unset. So set and unset. So it's an and not. Cool, I'll have to take these two up into the internal as well. Right, getting closer. So I just realized, got a bit of a problem. So we're on the stack of issues now. But so when we are trying to sort of find a leaf node for right, and we're going down, like we're looking at the bit set, see if the child exists, but we're never like setting it back, right? So if the child is missing, it goes into here, right? And then it sort of works out a new count, but it never sets it back. So yeah, it never sets it back. So here it should be like voxel map node. Hang on a minute. Yeah, why is these just called node? We should probably call it, yeah, it'll be fine. So we'll call it set, right? We call this one set. You pass in the hot node and you pass in the index of the child. So it's just child index. Cool. So I'm glad we caught that. That would have been really difficult to find, probably. Well, yeah, it would have been a bit, it would have caught me off guard. But, right. So the other thing was when we set a voxel, right, rather than going over and looking if they're all empty, like zeros, maybe we never have to waste zero if we had an unset. I don't know. Well, we have the bit set anyway, which tells us if it's empty or not, right? So we could have a zero voxel, which is air, but then, yeah, I think we maybe should. We've got enough voxel material indices, but the bit set will be there to like I guess make it quicker or something as well. But yeah, so we're basically saying, right, voxel map node set. You get the hot, which houses the exist bit set. You mutate that. Then right, so it could never be empty in this case. You need an unset. So, oh well, that's the thing, right? If it is a 0, yeah, let's do that, right? So if it's a 0, so it's more likely going to be something. That's a set. Else, it can be an unset. And then, how do you know if they're all empty? Well, you simply look. So you get this thing, you just call it hot. So voxel map hot. And you call it. So there's two U32s here. So you just say, right, if this and equals 0. Then we know that it's empty. And now we can remove the leaf node, and that's far better. Cool, very nice. Right, so now we can go back to this remove leaf node. So we're just traversing down from the top of the tree, and we eventually reach the leaf. Now we simply check. We just want to do a reverse for loop. So I don't want to use unsigned or not. Yeah, I'm not fussed. So we'll call this the reverse index, and we'll just do it the other way around, right? Not too hard. So parents count, something like that is. Yeah, I'm not sure why I needed to do something that fancy. Like, it's just. That might be it. Right, so index is take our index, take 1. Okay. So we're coming from the back, and we're literally just looking at the parent node indices. So I guess you get your node index, and you want to like see where the child was inside that parent. So we already kind of worked that out here anyway, right? So you're just checking whether it exists or not as well. And yeah. So you just get, right, there's two things you do. Parent node indices and parent node child indices, something like that, okay? And you just backen these guys up, which is super cool. Sorry, that is child index. Cool. Now, you fish this guy out. Now, all you're doing is getting the... You're looking in the bit set, and you're saying you're unsetting it. So you do that voxel map node child unset. You find the hot. So you do also have to free, right, the existing data as well. It is part, yes, it's fiddly, but it's possible. It's not that bad though. So you pass in, so you unset it there. Right, you also have to get the child and deallocate its thing. So that would be, so the child cold. So where do you get your cold as well? You get these guys. Right, so work out the child node index. That one you want to free. So that child there has a reference to its children, and that needs to be completely gone now. So this is where you save it is a leaf, which it's likely not to be a leaf. Well, in this case, it's more likely to be a leaf at first. But yeah, anyways. So if it's a leaf, you basically just do that voxel pool mark for deallocation these so you get the start index that comes from the auxiliary. So voxel map node auxiliary. So you mark for deallocation all those material indices, and that's done there. Then for the other one, you want to mark for deallocation all of its nodes, basically. Now, how do you get the range? Good question. You need the hot, and the hot will tell you it has the bit set right, and you can do a count on the hot. That's right. So child hot. Cool. So we need a range. The start index would be, the range, sorry, would be start index and start index plus children count. Cool, but it needs to be rounded up to the nearest Yeah, it needs to be rounded up to the nearest cache line though, but we can't know that. Oh, no. It would do it automatically in the allocator, which is cool. Because it's aligned to a cache line, so it does it for us. That's very good. Right, so that will deallocate the node, the memory that the child is pointing to. Then we unset it in the parent, and then now we need to shift remove it out of existence. So we need to find out. So we need to do the inverse of this basically. So effectively you want to say, right, if hot child exists equal 0 and hot 1, then what we've discovered is we can actually continue and then just delete this from existence. Now, sorry guys, my son is making some noises, a little bit ill. Let me just go and check on him. I'll be right back. But yeah, any questions guys, feel free to ask away. I'll be up here. Welcome back, everyone. How's it going? Oh, very good. Right, so we're just trying to wrap up on that code, which is basically going back up the tree and deleting the nodes if there's no more children or no more siblings. So, as we change a voxel and it goes to like air or something like that, we effectively say, right, delete the leaf node, and then it traverses down the tree, finds the leaf node, then goes back up the tree from the bottom with all of the parent indices, the indices for the parent nodes, and effectively finds the child within that parent finds the child within the parent and deletes the child auxiliary data. So like it's the child's children nodes allocation and the child's voxel material indices allocation. It deletes those and then it unsets the child in the bit set of the parent, and then it says, right, if now there's no more children, continue back up, right? And then here we're going to break. It's going to be cool. So here we just do a shift remove. So we want to be, I think the copy count is, oh no, it's many, isn't it? Right, it's a bit fiddly, but let's do this. So you get the number of children in the node. In the parent node. Now, you find where the child is in this array. And you do a child count, take 1. That's the number of elements. So if you're at the back, you'll copy in none. Something like that. I got to be careful here. So if you've got 5 children and you're at index 4, you do 5 take 4, take 1, lose 0. Yeah. So that will be, ooh, 5 take 4, it will now be 0. That's what you want, isn't it? Copy nothing over. Yeah, because the child count would be decremented. Right, it's no longer a take 1 because you've already decremented it because you've unset something there. Cool. Right. So this would be, so where's the start? That's a good question. The start comes from the auxiliary, which is there. Now this is actually doing a shift right. We actually want to do a shift left. And so this shifts the elements to the right to insert, whereas we want to shift the elements to the left to remove. So the first one is so this is just mem move, but it's a wrapper, so it does like it does it in elements rather than bytes. And so we're saying, right, the destination is where the child is, and we're saying, right, take the ones from the right of that and copy the rest of the elements in the array on top of where that child is, so that the child gets removed, right? And then voila. Amazing. Cool. So that's basically the code that we need. So that's the removing elements done. And we return a true at the end. Super cool. Like that a lot. Right, so that's the next thing done. We're getting very close now. So copy in a 3D span of voxels used to copy or generate from file. Yeah, that'll be a cool one, right? Can you copy in like just a group of voxels rather than doing one voxel at a time would be long. It's very slow. How do we handle root node references? Currently they don't get cloned. Right, so that one's actually a problem. The one like 3 is not a problem. We can always add that in a bit. There's some stuff to think about. So let's handle 4. So root node references won't get cloned. And that's because it was being passed into the function and it was kind of like invisible, but now it's here. I think it's possible. So what we need to do is simply ask a question. Do we need to copy the root node? So you need to do this sort of like needs copy thing. And the number of children never change, but yeah, so we would do something like so if one child is missing, they're always missing, and we keep going on, right? But if that needs a copy. How far until we get the system on? We're going to try. How far we are trying to try the system on the CPU and do some basic debugging. I guess we missed all the fancy GPU shader parts. No. So I've already done a voxel ray tracer. So yeah, I'll answer both those questions. So we already have a voxel ray tracer, but it's for voxel models. So I've got a Magica voxel importer. You can import models from there and you can render them. I was going to be using that renderer to render the map, but after many iterations of trying to figure out how to render this map, it was apparently clear that what was better is if we just have this voxel map structure and it's a tree, and you simply ray trace against that full screen. So we are going to need a specific renderer for this stuff. So that will come when we have sorted out this data structure, and when we go to we're going to do a very basic generator. Like it's not even going to be a proper generator, but just one which will generate a random map or something like that, but very, very basic. Maybe a sine wave floor, that's it. And that will, yeah, then we'll write a ray tracer for that. So that'll come. Hopefully not too far in the future. Hopefully before the baby arrives. Yeah, we'll see. There's baby number 2 coming in less than 7 weeks now. Beep, 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 beep. So if we need Yeah, so I was thinking like, so if a child is missing, yeah, so that was the thing, right? If we need a copy, and why do you need a copy? Copy on write, but we're not writing. So the only time we write is when right, let's think about this. So if you have, go ahead and do some drawings. Do, 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 do. Right, so you have this is the root node. It's not really a binary tree, but here we go. You got a child, and these are sitting in their own, they're siblings to each other, right? They're in an array. Now, when you want to create that a child is missing, so the child is missing, this node needs now to be copy on write, right? And that's only when so I'm wondering if the needs copy actually needs to be done. Like, you don't just need to copy the whole tree. You only need to copy the tree if the child. What's the way of saying it? Yes, if the node, so it'd be hot. So that changes right there. So hot gets changed, so it gets mutated. These are all read-only ones. That's read-only. That's a mutate. Yeah. So really, needs copy doesn't need to happen. Needs copy only needs to go here. And so the child could be missing, but you could find out that if you just add another child, it doesn't need a reallocation because we've aligned our allocations to a cache line. So you can still fit some more elements in there before you go ahead and right. But you need a copy if it hasn't been mutated this frame yet. And then when it has, yeah, because it's copy on write, isn't it? Okay. So you don't want to keep doing a bunch of copies if you don't need to. Cool. Right, I'm glad we caught that because that means it's doing less copies now. I think. Yeah, it's only doing a copy when it needs to. That's very good. Now, so the root node itself. No. No, I think you might need that back where it was. So if you change this allocation, which this will point to in memory. You need to change, so you reallocate it somewhere else. You'll need to change this node's pointer. So that means the other ones which are pointed to it will see the new allocation rather than the old one. And so yeah, you do need the copy to be there. So just always copy, yeah. If you're going to go down to mutate, I think that's right. Bum, 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 bum. Yeah, we can always improve it later, but yes, the idea, right, is you want to say where is it? Do this. So if map root node but then I guess it would check here if this needs a copy. Yeah, okay. Right, it hasn't been changed this frame. Just allocate me a new root node location. It's crazy. Yeah, so we're going to allocate basically 8 nodes, right? But then only one of them is used because it's the root node index. It's the root node which has no siblings, right? Actually, this could be made better. Why have a root node when you could just store the root node in the tree? Mm. You could store the root node in the tree. So the best thing about it is you could say, yeah, you just store them inside the tree directly. That'd be kind of nuts. So the way around it is you do your voxel map node hot, root hot, cold. And then that way you don't have an index which these still have the same problem. Maybe. Yeah. Because this, you can sort of get the pointers to work, right? You just basically point to the map builds, but here we're using a node index to do stuff. And that isn't gonna map well. So yeah, just go back to doing the root index thing. Okay, so back here. So we could make this a function because I think it might have to be, you could say if map is equal to U32 max maybe. Then We just want one. Get the start. Da, 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 da. Yeah, so where is there being a... Yeah, we've got to figure out what is creating the... we might have to set the allocations up here. Yeah, let's just get this sorted out first. So it's doing... Oh. So that'll be the new root node. Basically, you want to get the old data and if the old data exists, if map then just mem copy that over. So the cold and the hot data. And deallocate the old one. So map right, and then the just set up equal to new. Cool. So one thing that we didn't kind of handle. So yeah, I guess we can tick this one off now. Ta-da. Yes, another root node gets reallocated, a copy on write basically. The issue is when do the child elements ever get allocated in the first place? So if a child is missing, it will... Right now it's 0 initialized, right? If the child is missing, is 0 initialized, and then... But what's the point of doing that? Well, you can 0 initialize the hot data, right? That makes sense. But the cold... If child is a leaf, so it's most likely the other way around. We can just allocate it here, right? So just do your things. It's a little bit different, but yeah. Do this. And you do your set of false. Cool. So I guess you just do... you could... how many children do you want to do initially? I think you want to do just one. Do one for now. But yes, they'll do a round up to a cache line. So that'll be fine. But yeah, we could probably get this going a little bit better. You can probably say, right, Star index, is that around here? And there you go. Cool. Nice. Right, so I'm glad we found that issue as well. Right, so we're getting very close to this data structure to be ready to use to like generate a map, basically. Like it seems pretty close. We should probably do the initialization. That would be helpful. And I'm quite happy with how this has turned out now. It's still a bit complicated, but it's far less complicated than it would have been. Which is a good trade-off. Always. Man. Anyways, very close. So frame initialize. Because it's copy and write, we have this bit set basically, right? So yeah, we probably want to know like how many nodes. Yeah, what did we do there? Oh crap. Wind it back for a minute. Deleted something. Some more code which might be useful. Or maybe it might not be. Put that back. But yeah, there was some other code somewhere here. Yeah, we can work out the maximum number of nodes we're going to have, I think. You take... something like that. I think you do that. Right, this is good. So let's do the initialization. Let's get this out of the way. So we want the custom allocator, that's for sure. We want the dimensions of the map. And so that would just be... Now you do want to do your lovely little assertions. So that would be... all so I guess equal. I missed the equal, wasn't it? Mod s equals 0. Cool. And the other one was that it must be greater than equal this number here. Cool. So that's the dimensions. Then you've got the root node index will just be U32 max. So that will be initialized when you first try and mutate the map. Then we have this bit set here. So the number of nodes that you'll possibly need is based on this Now it's probably... It's a lot. No, actually, this gets allocated from the global node indices. So there's a pool where all the nodes are allocated into. So actually, that's be U64 divide round up. So pool, gotta find me the map pool. So if we have multiple instances of maps that we share between it, basically. I don't think we will, but it's capable of doing that. So we get the node capacity. Would kind of be nice to store it in there. Right, let's put it in here somewhere. Okay. So if we go back to the map mutator in it, we'll just do the pool nodes cap and then size of bits. No, it's not size of bits, is it? Yeah. Yeah, what do we do for that bit set down below when we allocate it? What do we do? Here's this. Alright, I just messed it up a bit. Alright, then we need the allocator, obviously. And that should all be zeroed memory as well. And amazing. So when we do an initialize, so we probably want to do like... Sorry, frame initialize. So when a frame starts, we want to do a zero element many. Zero all these elements for me, please. And you're zeroing all of that, right? Yeah. Cool. Right, so this should be the data structure in place right now. So this should be ready to be used. Yeah, so we should be able to basically generate a map into there and then try and render it. That's probably what we should do next, because getting stuff on screen is probably more important. But the basic idea is we want to have a big old map which is a kilometer by a kilometer blocks, and going up by maybe a quarter of a kilometer in the sky. But that takes a lot of data, and a block, by the way, is 16 by 16 by 16 voxels. So it's stupidly big, but that's the plan. So we'll generate something smaller first, and so we need two maps basically. We need one map which will be at a block resolution, right? So it's thinking about whole blocks, and the other map will be at the voxel resolution. So all of the game logic will work with pretty much the block map, but the game will produce a voxel map for the renderer to actually render, and that's going to be the high detail. And some of that stuff is going to be probably loaded off the screen and stuff like that. But yeah, it's things to think about there. So the voxel map gets generated from the block map. I think that's the plan. But I think it's good to just get rendering something as soon as, really. So what we can do, get rid of all this silly to-do stuff. This voxel mutate I think is a good idea about caching, but it's extra code we don't need right now. We'll look at this block map later on. That's the plan of doing the other map. But the voxel map mutator, that's what we just call it. It's just the name we landed on. Okay, so good. Good. Right, we're in a good place there, I think. So what if this is not compiling? So voxel internal. Nice. Right, so we go to the build script. Do we have any... is this the game here? Think so. Yeah, game DLL, this is it. So we need to add a new one, voxel. And we need to compile... So these ones are for what exactly again? Yeah, these are dependent on the code gen. Yep, so there'll be another one for voxel. Right. So, now inside game, did we do any voxel map stuff in here? I think we did. Yeah, so the world is going to have its own voxel map mutator. Let's call it map. Not really happy about that name though, but it's either you call it voxel map mutator or you call the other one voxel map view, something like that. But anyways, we can rename it some other time. Hmm. Yeah, what sort of things can we do? You could call it like a voxel map ref, and that will be... Yeah, maybe just call it ref. Because you never really... Yeah, then this one you can just drop the mutator thing off it and then voila, right? That would be a lot nicer, wouldn't it? So voxel internal. Voxel C. Yeah, it's much nicer. I'm happy with that. Cool. So we go to the game. So here's the idea, right? What is this trying to do here? Oh yeah, it was a completely different API. So this is when we render. So in the payload, hang on. We just want to take a reference. See, it used to take like a copy of a bunch of pointers, but now it literally just has an index to the root node, and that root node will be copy on writed basically in the next game frame. So the next game frame will point to a new tree, and but only when it's mutated part of that tree basically, right? So a lot of the old data is still referenced and reused, and the old data is kept alive as well. So we want to do there'll be a function called ref. So it's now called voxel map. I just realized as part of that rename, we should call it ref. So you take a reference to it basically, right? Makes sense. Cool. So you just do voxel map ref, and then you basically send that into the graphics payload. Very easy to do. Now, yep. So what we can do is have a bit of fun. We can now right, to do start from here. This was incredibly old. We've gone through many iterations now since then, but I'm glad we're coming back up the stack. We should be able to generate a very, very simple map. Hey, what is this? Oh yeah, no longer do we insert any. Yes, we was going to do it by rendering a bunch of voxel model instances, and there were so many that weren't going to fit in the payload without doing something really crazy. And so then I was like, you know what? Let's generate them after the payload has been retrieved, but on the render thread. Yeah, but then it's still going to put them in the payload. I've got a reason why I did want to do that in the end. There was some reason. Anyway, bad idea. So now we have a map instead. Now, where else is the map? Right, so map initialize. Okay. So we'll do a smaller version of the map, right? Just 256 by 16 by 256. So, yeah, maybe we can do smaller. Maybe let's just do 64, right? Just keep it nice and small. And we're going to do, oh, I've already kind of done it, like a little sine wave. Amazing. So we're just going to say voxel set, right? And we're simply just going to set in 1. So it should be 0 initialized. Maybe it's not. That's a very good question. So when we allocate those new, when we allocate those new nodes, where are you? When you allocate the new nodes, you didn't zero anything. Nah, but does the heap allocator do that? Because, you know, the whole idea of... No, but the heap allocator can't do it because it's just working on metadata, basically. But yeah, we should ready zero everything for you. That's the way my allocators typically work, right? 0 is initialized. The way to go. So we actually want to do a mem set. Well, so they're stored in where? They're stored in pool node hot element range start, and we want to zero element range There's a different number of elements depending on the array. Let's just memset 0 that thing. It's byte range 0x00. Alright, so you just do that, and for cold as well. Oh crap, it's not gonna work. No. Wait. The element one was gonna work. Because it's designed for the mat. Yeah, it's gonna work. So the hot is twice as big as the cold. And because the capacity works off yeah, it effectively always does a max between the hot and the cold basically, and the allocator works off that allocates a byte range for the biggest one, and we do a divide here so that we get an element range which will map directly into these two arrays. Right, that's fine. So they're parallel arrays, right? Okay. And the final one was these indices. We definitely want to so it's and then it's something like that. Right, so now they're zeroed, right? So I don't have to worry about that being a problem. So yeah, now we can just make the map. We go over and store along the XZ plane, but we modify the Y, and we're just going to poke in there a bunch of ones. Cool. Man, this is great. So yeah, I'm not sure if the frequency and scale are good enough, but we'll find out. Yeah, they'll go up. Well, yeah, this is in voxels. And so maybe we scale it by 16. Because that'll get you like up and down 16 voxels, which is like, you know, there'll be 2 blocks in the end it'll go. So it'll be quite cool. But yeah. Right, so the other thing that we need to sort out is cool. Yeah. So we can now write like what we'll be doing in the next streams basically. So let's go to that voxel plan. So maybe I can check this in tonight and get something in. Does it still render? It still compile? Maybe not, right? See what happens. Oh no, because I would have broken something else as well. But what's this all complaining about? uh, I think core shared gets included. Ah, come on, it's right there, isn't it? What are you complaining about? So what includes core shared? Yup. Ah, right. Oh, interesting. Voxel map mutate game.h. Man, I'm so glad we changed that name. That's good. More expand. Oh, redefinition. Oh, that's amazing. So now Voxel Builder, so Vox Builder, which takes in the magic of Voxel files. This guy, all that Morton stuff that we sort of copied, can now just be completely removed, which is amazing. Because it's in the shared header file now. So good. Cool. What else we got in here? Graphics, material palettes. Oh yeah. So I've gone and done a thing where I've made it such that my material palettes are now variable sized, and it's better, but like it's probably broke stuff now. So hopefully it's not so bad. Like I know it's broken some things, but probably not everything. Like it's broken the palette editor. That's now not going to work, but we'll get that working again when we work on entities. But I think it's possible. Right, let's say we had two files getting errors at the same time, so it kind of just interleaves all of that. So game.c, oh, right there, isn't it? You don't like a reference? Oh, okay, so that's a reference to a reference. Yeah, okay, right, I got you. Cool, so 1127. Right, it's not going to be that performant, but it should work. The main thing. Hopefully the boot times are not that bad. But yeah, we're doing a small map, so it should be cool. What else? So graphics VK has some more issues too, apparently. Oh, it say search and find, but didn't find anything. So BPV, what does that one mean again? Oh, bytes per voxel. Right, I see. Yeah, I wonder whether we should. Hmm. Yeah, this wasn't changed, was it? Yeah, because the material words aren't going to be enough now. We could just hard code it to 8 though. Bytes per, sorry, bits per voxel, wasn't it, or something like that? Yeah, so we did 8. Let's see how far that gets us. Ooh, there's a bad define in there. Let's have a look at that one. 9. Don't do this, GLSLC. You silly compilers. Bad argument. Does... Right. GLSLC, does it support variable args? And it'll probably be like, no. And you'll be like, come on. Come on. Look. Every time, there's some basic feature it doesn't support. Why do they do this? Why do we take this language seriously? Crazy. Like, why is this considered a serious shading language? But yeah, that's where you can use like a preprocessor. Yeah, you know, you pre-process your shaders, right? That's one way to solve these silly problems. But yeah, so now I can't have a thing which allows me to change it based on the language now, or because they don't want to support that. It's nuts. Right, but we're not using it anymore. Okay. Right. Thankfully, we don't have to use it. But man. So this might not be declared. And so I think that might be in GPU shared. Of course it is. Man. So these are all the packed vector stuff, basically. The joys of sharing code between CPU and GPU. I guess we just wedge that in there. Wait. Where can I wedge it in? Yep, then I just want to say, hey, if you're jealous, do this for me. All right. All right, it compiles, which is pretty good, but we're failing now because, oh, it actually tried to do something to do with the voxel stuff, and pretty amazing. We could open it up in the debugger. Right. Yeah, let's open up in the debugger. Man, it's been a while since we've been running the code. Glad to be back here. Is it E32 max? No. What's hot? What's the null pointer? Oh. Oh, okay. Right, so we just haven't initialized the subsystem yet. Amazing. So basically, we've got this thing called voxel cache in it, right? And yeah. So game C, so somewhere around here we can just throw it in. Okay, so yeah, I'm not sure about these chunks and all that. I think that's going to get removed, but let's just put 1,000 in there anyway. Yeah, let's just say there's 1,000,000. And let's say there's like 8 rollback frames or something, I don't know. Cool. So we do that, they should all be initialized. Right, so now it's complaining that block ID is 1, is not in the free list. Yes, this is the new allocator I've wrote, but it's not. Yeah, been tested yet. But it's cool. Shouldn't be too hard to fix that. There's a heap allocator where everything is aligned to some fixed alignment specialized when the heap allocator is made. So we can do stuff like aligning things to cache lines. Aligning multiple elements to cache lines. And we don't have to pad things out. The allocator can automatically pad it out for us, which is cool. Amazing. Right, so unfortunately there shall not be a stream on a Thursday. There typically is streams on Thursdays, but there's stuff going on at church this week, so I won't be in this Thursday. And also next Thursday as well, it's my wife and I's anniversary. So I won't be in that Thursday as well. Basically, these past 4 Thursdays, I haven't managed to be streaming, which kind of sucks. But there's been stuff on. It's kind of summertime. It gets busy. But yes, Tuesdays, typically Thursdays, but not this Thursday, and Sundays, 7:30 p.m. GMT +1, and Fridays at 2 p.m. GMT +1. But yeah, next stream, we should be able to be working on trying to get this thing rendering, this voxel map rendering. And off stream, I'm going to try and get the rest of these compile errors sorted out, and these runtime errors. Get those fixed so it actually runs the game again, and we can actually just get going next stream. That'll be kind of cool. And so we will be doing a full screen ray trace through that node, that voxel node tree basically. So again, it's like a sparse voxel occ tree, but it's instead of an occ tree, it's 4x4x4, 64 nodes instead of 8. But yeah, so we'll just get the quickest thing going first, then a full screen render. We can check performance. If performance is terrible, we'll do some optimizations. But if it's all right, we'll probably just leave it alone. We'll see, right? But yeah. Awesome. In the meantime, guys, there's a Discord channel. We're going to come and chat. And there is also a YouTube channel, right? If you don't know the game that we're working towards the game. We're doing the map first, doing entities, then we'll get the basic, like a vertical sliver of the game, right? Start to finish. And then we'll keep expanding it out to the point where it becomes a slice, right? And then we'll go from there. But yeah, we're building a prototype, basically. That's the idea. Hopefully we can spend like 6 months on it. We'll see. We'll get to by then. But yeah, in 7 weeks' time, I've got my second son coming, so I'll be taking some time off then. But yeah, in the meantime, guys, you can also support the stream and the channel and the company as well over at the Ko-Fi page. This code is typically uploaded every now and then, and so you get access to run the code on your own local machine and have a play around with the code and see what's in the code base there. But yeah, thank you everyone. Appreciate you all, and I'll see you all on Friday hopefully, or if not Sunday, because Thursday stream is cancelled basically. But yeah, God bless you all, have a good night, and I'll see you all Friday. Bye bye.